start. So welcome to MGM course, and this is what we plan. So we completed GAN, and then there are variations of GAN, which is called WGAN, and then further variation which is called gradient penalty, and then core ideas more or less remain same, and with some architecture engineering you can develop many other variants of GAN which are very state of the art. Okay, so it could be style GAN, it could be giga GAN, and so on. So I'm not sure how far we can go there. We will start with first three topics, I guess, duality, and then we will use KR duality and so on. So so let us start. Content is quite a lot, but I don't think I will be able to cover. So in WGAN, what we will need is some idea of duality. Okay, so I don't assume that you have seen duality. Usually it's a topic in convex optimization. I will introduce you to duality, and that is used to derive something called KR duality. So in generative adversarial networks, we have seen that we start with KL divergence, and KL divergence as such is not tractable. So what we did is that we went to look for some variations, variational form, and we could get it via F divergence, and we use some idea from convex analysis there that we looked at the conjugate, and then we could use the fact that conjugate of a conjugate is the same function itself, and that gave us some variations in the F term there, and then from there we could derive some lower bound. Okay, and here what we will do in WGAN is that we will start with not KL divergence, but we will start with Wasserstein divergence, but actually it's a distance. So here our starting point will be Wasserstein metric. This is also used to compare two probability distribution, just like KL divergence. So but this will lead us to a different style of approximation. Okay, and this is something you are trying to learn in this course. Okay, how someone starts with some distance measure and does various kind of approximations and arrives at some interesting algorithm. So here to begin with, what we will need, as I said, is the concept for duality. So let us go back to convex analysis part 2. Okay, we have seen part 1 already, where you have seen what are convex set, convex functions. You have seen first order criteria of convexity, second order criteria of convexity. You have seen conjugate functions. Okay, let us start with convex analysis, and the first step is something called Lagrangian, and this is a simple idea. So Lagrange, some credit to Lagrange. So this is Lagrange, and he was born in Italy, but then he moved to France and he changed his name from Italian to French. He was mostly doing maths, calculus of variations. Essentially it's about optimization methods, basically maximizing or minimizing, but it's a more generic variant. So you also look into Euler, Lagrange, and things like that. He had contributions in analytical mechanics, number theory, and celestial mechanics as well. So one of the things, Lagrangian points are defined after him. So if you can recall some news, so Aditya L1 that was sent by ISRO, that through the Earth, and it kind of goes through this, and then it goes to Lagrange points. So Lagrange points, usually it means that this spacecraft will not orbit around any Earth or moon. It has its own orbit, as if it's like orbiting around nothing. Okay, so these are Lagrange points. So there is Lagrange point around Earth. There are like 4, I guess, I'm not sure, 4 Lagrange points between Earth Sun system. So it can just keep rotating on its own. Okay, so this is named after Lagrange. Okay, so he has a role here. when we define the Lagrangian. Okay, so that's why we. So this is an optimization problem in standard form. That's why we call it standard form. So usually you minimize a given function. In this case, objective is f naught x, and then you have inequality constraints, and you have equality constraints. So in this case, there are m inequality constraints and there are p equality constraints. So hi are called equality constraint functions, and fi are called inequality constraint functions. So obviously this I starts from 1 and f0 is called objective. So this is more or less all the optimization problem. Usually they look like that. Okay, you can capture any non-linear boundary and constraint set via these, okay, or via some equality constraint. So this is how people talk about optimization problem in a compact form. Okay, and usually it is minimized, but maximize can be negative. You do the negative and then you minimize the function. So only minimize is suffices to study. So what is about Lagrange, right? So Lagrange idea says that augment the objective f naught x with the weighted sum of the constraint. Okay, so as I have defined, these are constraint functions. So this is an equality constraint, this is equality constraint. So what it is saying is that you take the objective f naught x and you take a weighted sum of these guys. Okay, so these weights will be called Lagrange multiplier. So that's the idea of Lagrange. Okay, so according to that, this is what Lagrangian will look like. So so Lagrange domain, if you can see, is Rn. Rn is where the x lives, and Rm is for the Lagrange multiplier. So this is called lambda, and Rp, p stands for the dimension of the mu, which goes with the equality constraint. So let us look into this Lagrange. So this is first term you see is f naught x. Okay, that's fine, and then we did a weighted sum of the equality and inequality constraints. So these weights that you see lambda I are called Lagrange multiplier, and then this is, you call it nu I, it goes with hix. Okay, so this is called Lagrangian. So as you can see, given any optimization problem, you can always form a Lagrangian. It's a very simple thing to form. So this lambda I goes with each of the fi, right? So you will have as many lambda I as you have fi. So in this case, you have inequality constraints m of them. So lambda will be m dimensional, and then if you have p equality constraints, then mu I you will have to have p of them, and then it's p dimensional. Okay, so this is Lagrangian. And sometimes these lambda and nu are called Lagrange multiplier, but sometimes they are also called dual variables. Okay, so this is it. Given an optimization problem, I can form a function which is called Lagrangian. Okay, yes.
Are the upper bounds treated the same way as the equalities?
Are the upper bounds?
Like f(ix) less than equal to 0 is
You can multiply by the negative, and you can always adjust and make it less.
No, I meant so all the fi's are treated the same way as the hi's?
Treated means what? Fi goes with lambda I only, right? And hi goes with nu I. So yeah, it will matter, and also lambda I has to be greater than or equal to 0. So there is a constraint on lambda I there. Yeah, so you will treat them separately, because there will be problems where when you are looking at the dual form, it will depend on which of the, like, when you go to strong duality, then inequality constraints play an important role. So it's a good idea to keep those separate. Okay, so I will discuss something called Slater condition. So the point is that it is a good idea to keep inequality, although it looks like why did I need separately lambda and nu? That's a valid question, but inequality and inequalities play a slightly different role, so it's good to have different variables for them. Okay, so you form the Lagrangian, and so this is x, lambda and nu, and what you see here is infimum here, right? And infimum is taken over x, which was the domain of the function, okay, f naught x we wrote, right? That's what we want to minimize. So this infimum is taken over x. So if you do that, if you do infimum of the Lagrangian for x, then you define a new function which you call it Lagrange dual function, okay? Now this is sometimes students make mistake, okay? So there is Lagrange function and there is Lagrange dual function. So dual function is after the infimum of the Lagrangian, okay? So that's infimum of the Lagrangian, we call it dual, okay? Sometimes we just call it dual function, okay? Okay, so so this is our new function, okay, that's fine. So the Lagrangian, if you look at the Lagrangian itself, it's as a function of lambda and nu, it's affine. So I hope you agree with that. It's an affine. You forget about f naught because f naught x treat x as a constant. Okay. So if you see Lagrangian only as lambda and nu, so you can see this is just as if like lambda transpose some f. You are taking a dot product some sense. Okay. And m dimensional dot product. Here you are taking as if p dimensional dot product. So this is a linear in lambda and nu. So that's kind of easy to see. There we don't see any powers of lambda and nu, right? So so it is an affine function of lambda and nu. Now if we take an infimum of the affine functions, right? So what do you guarantee, right? If I take an infimum of the affine function, so last time I told you that the last time or the previous one, what I told you is when we were looking at the conjugate functions, then we said that regardless of what the f is, conjugate being the supremum of those affine functions is always convex, regardless of what the given f is. Similar argument is going on here. Now if I look at the Lagrangian, this is affine as a function of lambda and nu, and I'm taking infimum. So it's like as if infimum of affine functions. What can you ensure? So by the same argument, like supremum, we can now say infimum of affine function will be concave. Okay. So it is guaranteed to be concave. Okay. So the same picture you can translate. I did that on the board. I drew, if you remember, a lot of lines and took the supremum. Now you do it infimum. So it will be necessarily like bending downwards, right? So this is very easy to prove that g lambda nu, the Lagrange dual function, being, because this is seen only as a function of lambda and nu. Okay. So this as a function of lambda and nu could be seen as infimum over various values of x you take. There is some linear in lambda and nu, another value of x you take, another linear affine in x and nu, and you are taking infimum of all these guys. So it's guaranteed to be concave. Okay, so that's more or less settled. So our dual function is necessarily concave, and it does not even matter what the original problem was, because it's not even looking at f, right? Because f we are just taking pointwise value. So if our original function f naught x is not even convex, the dual is necessarily concave. Okay. Okay, so from optimization point of view, what is interesting to note is the dual function, which is g lambda nu, gives a lower bound of the optimal p star. So p star is our optimal value of the optimization. So basically p star is the lowest possible value of f naught x. Okay, so p star is the lowest possible value of f naught x. So f naught x, and this is the minimum possible value of that. So this is what p star means. Okay, this is called primal optimal. Okay, when I'm solving the problem in the x variable, then you call primal optimal. So that's why you call it p, and star is for optimal usually, right? So what this result says is that given an optimization problem, you form the Lagrangian, you infimize over x, and then what you get is g lambda nu. Then this g lambda nu acts like a lower bound. Okay, it's always lower than your optimal p star. Okay, and this proof I am going to skip this, but it is there in the slide in the interest of time. It's a very simple proof, just this much. Okay, so you can have a look, you can pause and have a look later on, or you can look at the slides. But what is important for us is that, okay, this is true. So dual function always acts as a lower bound for the primal. And as an exercise, you can try forming Lagrangian and the dual function for these. Okay, so as you can see, you have to take, in this case, to form the Lagrangian, there is only equality constraint. So what you will do is that Lagrangian will be x transpose x plus, and there is equality constraint, so I will use the nu. So nu transpose times ax minus b. Remember that standard form does not have anything on the right hand side. So you have to be careful that you should bring b on the left, and on the right side of the equality or inequality you must ensure that they are 0. Then it is in standard form. Okay. Okay. So you can form the Lagrangian dual function, and you can show that it is indeed concave and things like that. So these are just to practice. You can also try this guy. Remember, in the standard form says that the inequality constraints are always less than or equal to 0. So here you have to be a bit careful. You have to multiply by the negative and then translate this to minus x less than or equal to 0. Okay, and then your minus x is your one of the fi inequality constraint. Okay, and then you form the Lagrangian, you form the dual function. Same here for the equality constraint, you have to bring b on the left hand side. So you can do some practice of that. Conjugates we have seen. There is some relationship on how I can use conjugate in the when I'm constructing the dual, but that is not essential for our talk. So you can see these some examples of these later on. That is not essential right now for our talk. Okay, so I'm going to skip these things for the moment and pick things that are really okay. So we have seen Lagrange dual function, that is g lambda nu gives a lower bound for p star. And what is the best lower bound? So now I know that g lambda nu is less than or equal to p star. So this gives me an idea that that why not maximize this? Why not find a max of this guy for lambda and nu? And I want to go close to the p star. So p star guy is here, and g lambda nu is somewhere here. So why not maximize? So I will approach p star. So I can solve my original problem via the dual, right? So that's the idea of duality, right? In duality, you solve your problem in different way. Okay, you go to the dual approach, right? So this is a very straightforward idea that I know it's always a lower bound, so I will maximize and see how far I can touch p star. Okay, and so so we can form another optimization problem which is corresponding to the primal optimization problem like this. Let us maximize, and obviously this is maximize over lambda and nu because this is a function of lambda and nu, and maximize this, and let's see how far I can what is the lambda star and nu star in this case. That gives me the maximum value. Okay, and good thing for you is that g is concave. So if you are doing a maximization problem for a concave function, the uniqueness is there will be one maxima only. Okay. Okay. So original optimization problem, as I have seen in x variable, is called primal problem, and then we have this. If we solve this maximization problem with and find lambda star nu star, which is the optimal for which it's maximized, we call it dual optimal. Okay. So then there is a question of let us say d star denotes the optimal value of the Lagrange problem. That is d star in our case will be it will be g lambda star nu star, right? So lambda star nu star for which g became maximum, let us call that value of g d star, and we call it we can call it dual optimal, right? So in general, we can now say that d star is less than or equal to p star, obviously, right? Because d star is some g value, and g was always less than or equal to p star. So that's called weak duality. So it is called weak because you are less. Okay, you may be less compared to the primal optimal, and if you hit the equality, then it's called strong duality. Okay, so we can note this thing, that the dual d star is less than or equal to p star. Okay, that's weak duality. and and this is called optimality gap. So how much gap you have, right? You are going to solve your problem via the dual, and you could go as close to p star as possible, and if you could not make it equal, then you will have some non-zero value p star minus d star. P star minus d star will be positive, obviously, because p star is always greater than or equal to d star, and we call this optimality gap. Now obviously we will be also interested in strong duality. When I'm forming a dual problem, indeed I want to go close to the primal optimal, because someone gave me a problem in the primal variable actually, right? I changed the problem and so on. So it is ideal if I can give the primal optimal solution which is close to the primal optimal, right? So if d star is p star, then we say that strong duality holds. Now as we can guess, strong duality does not hold in general, and if the original problem is convex, then we usually, I'm not saying it's a guarantee, so there is something called Slater condition we will see, and so usually we have strong duality with quotes, okay, under quotes. So there is something called Slater condition. So Slater condition says that if there exists in X, in the primal X, right, primal domain, such that fi of X, what was the fi of X? These were your inequality constraints in the optimization problem. So if it so happens that there is one X, at least one X, for which all inequality constraints become strict, if you can find that X in your domain, and you don't see anything about the equality constraints, okay? So this is where I said there is some distinction that we make with the inequality and equality constraints, especially in Slater condition. I am only looking at the inequality constraints, okay? So if you can find some X for which all the inequality constraints become strictly less than 0, for all the inequalities I equal 1 to m, then we call this a Slater condition, okay? So that's a condition. And why I introduce this? Because I'm looking for case where strong duality holds, okay? So Slater condition will help me finding those. So this is what Slater's theorem says. There are two things, Slater condition and then there is Slater theorem, okay? So Slater condition is just like just this statement, okay? And Slater theorem says that if the primal problem is convex and if the Slater condition holds, then strong duality holds, okay? So we take this as a statement that if the Slater condition holds and the primal is convex, then we have a guarantee that if I solve the dual problem, I will reach the primal problem, okay? So Slater condition, and there are slight variations of that as well. So in Slater condition, if it so happens that in the inequality constraints, in the inequality constraint only, okay? Slater condition only looks at inequality constraint. So if it looks at the inequality constraint, and what about some of the inequality constraint functions, which are some of the fi, let's say, from 1 to k, happen to be affine, okay? Then in that case, Slater condition says that, again, you don't look at those guys, just look at those fix in your inequality constraint, which happen to be nonlinear, non-affine. Only for those cases, if you can verify that there exists an x for which is strictly less than 0. So in this case, we are assuming that k plus 1 to m are those guys for which fi were not affine and they are from inequality constraint. Then if I can find such x which for which they are strictly less than 0, also it's enough, okay? So as you can see, Slater condition only looks at the inequality constraints, right? So if I'm given a problem like this, x transpose x and ax equals to b, you can see there is no inequality constraint at all. So only thing you are supposed to check from the Slater condition or the Slater theorem is whether the primal was convex or not. But it is indeed true that the primal is convex, because from double derivative test, I see that double derivative of this guy x transpose x is identity, and identity is positive definite, all eigenvalues greater than 0. So indeed the primal problem is convex and there is no inequality constraint, so by default vacuously Slater condition holds, okay? So when you have a problem with only equality constraint, you only need to check whether the objective function is convex, and that's it. If it's convex, then you can easily go and form the dual and solve the dual and you are safe, okay? Yeah, the dual optimal will be primal optimal, okay? So you may try these examples. Obviously our goal is a bit different here, okay? And similarly, you can try for QC, These are just examples here. So quadratic objective with quadratic constraints. Here also you may check for which of the cases Slater condition holds or not. So I can skip some of these guys. So it does not mean that if your problem is not convex, Slater condition won't hold, okay? So this is a non-example that I may have a non-convex optimization problem, and yet strong duality will hold, okay? So there are non-examples. So it's not a necessary and sufficient. Slater's theorem is not a necessary and sufficient condition for strong duality, okay? So there may be problems which does not satisfy Slater's theorem, but still a strong duality holds. So these are some examples here. I will just skip those. Okay, so the reason why we looked at duality is there will be a case where we will look for when is infimum of supremum is equal to supremum of infimum, okay? So Inf-sup is equal to sup-inf if yes, when. So this we will need in the WGAN. So let us see the standard optimization problem, and this is what we are asking for, right? So strong duality says that D star is P star, that we know, okay? And what we are looking for specifically for the Lagrangian, so this Inf-sup is specifically for the Lagrangian. We will form Lagrangian in the WGAN. So so that's why we are focused on, let us say, whether sup-inf of the Lagrangian is equal to Inf-sup of the Lagrangian, okay? And and strong duality is assumed here. So I am assuming that strong duality holds. So D star is P star. So what I have to show is like D star is indeed equal to sup-inf, okay, and P star is indeed equal to Inf-sup. But if you see the first one, there is nothing really to prove, because D star, the way it was defined, it was exactly like that, right? So if you remember, if you recall the first equality, what did we do? We formed the Lagrangian, we infimized, then we got the dual function, and then we know that I did a supremum of the dual function to get the D star. Okay, that's how I get. So this is by definition, D star is sup-inf of L x lambda nu. And the middle one, D star is P star, is because I am assuming that strong duality holds. So that's also done. The only remaining part now is this guy, whether P star is infimum of supremum of the Lagrangian, okay? So this is also straightforward, okay? So let us see this, let us see. So what I have said, first one is by definition, middle one is strong duality, so all holds, right? Now to show the last inequality, this guy, what I am supposed to show, if I can show that the supremum of the Lagrangian is this, okay? So supremum of the Lagrangian is just this guy, and then from there it will be evident that if I further go and do the infimum, it will be indeed because if you see this term, this is indeed looking like the original primal problem itself. So whenever these inequalities are satisfied, equality are satisfied, I get f, and it's infinity otherwise. So essentially it is the primal problem itself. So what it means is that if I do supremum of the Lagrangian, I over lambda and nu, I actually I am with the primal problem, and if I do further and go ahead and do the infimum, as if I am doing infimum of this guy, which was actually the optimization problem itself. So yeah, there is a slight correction, I guess, with the notation here, as you can see here, with the notations that I have F5 for GI, and this is F naught x in our original notation, right? So this is exactly the original problem, right? F naught x and GI x less than equal to Hij x less than equal to 0. So up to supremum I get the original problem. If I am further going to infimize, this is exactly the same problem like infimizing this guy. That's it. So only thing we are supposed to show now is that supremum of Lagrangian is indeed the primal problem itself. Okay. So we want to prove this, okay? So I just copied that from the previous slide. We want to prove this result. So let us see. We are supposed to look at this, right? So let us look at the Lagrangian, and this is our Lagrangian, and we are supposed to supremize the Lagrangian over lambda and nu, right? So what is the supremum of this guy? That's the question, right? What is the supremum of this guy over lambda and nu? So to compute the supremum, what are we going to do? We can take the gradient of L and we equate both to 0. So and since we are doing supremum over lambda and nu, only lambda and nu are our variables. So we will take gradient only with lambda and nu. X is like static because this is the optimization problem only with lambda and nu right now, because we are doing supremum only over lambda and nu. So so that's the standard thing. We go and look for the critical points. So we go and calculate the gradients and see where the gradients are vanishing. That is the potential place where the suprema will be achieved. So we take partial derivative with lambda I, then we get Fix equals to 0, and partial derivative with respect to mu I, where we get Hix equals to 0. Okay. So it turns out that it is a linear programming problem because it's linear is linear in lambda and nu variable. Okay. So this is not a surprise that the optimal is being achieved on the boundary, because if you look at the boundary, because this is a kind of a we may think of these as some kind of a boundary being decided by these guys, right? So this is an LP. So what it says is that wherever Fix equals to 0, okay, the extrema will be achieved on the boundary. So so this region, your feasible domain, are decided by Fix less than equal to 0 or and Hix equals to 0. So this is your domain, the constraint domain, where you are looking for minima of your function, right? And this being a linear program, okay, so the program means linear optimization problem. There is no surprise that the minima is achieved on the boundary. Just to give you an intuition why linear functions achieve minima on the boundary, let us say the 1D case. So we have A and B, okay, and regardless of which linear function you draw, this linear, even like constant, you will see minima will be on the boundary. So minima of this guy in the constraint set A and B is always on the boundary. This guy minima is on the boundary. Okay, for this guy the minima is on the boundary. Even if it's a constant, I can say still that minima also exist on the boundary because it's a constant. So in all cases for a linear program, as you can see, the minima and now you can extend this in the 2D case, where you may have some region like this, which is your constraint set. It does not have to be like square or something like that, and you can say that this is your some plane, because affine functions are like that, or this is some plane like that, and necessarily minima will be achieved on some of the boundary only. So boundary in our case is exactly when Fix equals to 0. So this is not a surprise. This is telling me that indeed the inequalities are saying that these guys you have to be better inside, but then equal means that it kind of looks only at the boundary now. Okay, so that's not a surprise, and that indeed the minima is achieved on the boundary. So what we found is that Fix is forced to be 0, Hix is forced to be 0. So if I put all those Fix go to 0, Hix to be 0, what I'm left with is f naught x. Okay, so what I'm left with is actually the primal f naught x, and the constraints obviously are always there. So Fix less than equal to 0, Hx less than equal to 0. So what I have essentially proved is that the supremum of the L is essentially f naught x. Okay, f naught x, right? All of you agree with this, right? So supremum is nothing but the f naught x itself, because this forces Fi to be 0, this forces Hi to be 0. So essentially the supremum for supremum of L, then I am just left with f naught x basically. Okay, because this is an optimization problem in lambda and nu. So supremum of L over lambda and nu just is f naught x, and these things were already there as part of the domain. So what this says now is that this is my primal problem actually, and if I go ahead and do the infimum, then obviously doing infimum of these is the original optimization problem itself, so I get a P star. Okay, so so in that case, what did we really achieve so far? So let us go back to the inequality. So what did we say is that this guy is P star, and D star being sup-inf of L is already by definition. And if the strong duality holds, then what we now conclude is that the sup-inf is equal to Inf-sup. Okay, this is what we need. So this we will need in the WGAN, that sup-inf is Inf-sup, because it will help the calculations if we flip this Inf-sup there. Okay, so let us go to WGAN now. So we have some practice. So WGAN, W stands for Wasserstein. So his name of Leonid Wasserstein, born in Russia, and mostly working on dynamical systems and things like that. Now let us define Wasserstein distance, just like we define KL divergence. Now let us see what this divergence means. Okay, so this is sometimes also called Orth-Mover distance, and it is used to compare probability distributions in optimal transport theory. So optimal transport theory is a big area in itself, and there are a lot of applications as well. Also in generative modeling also actually. Okay, so we will see that a bit later in like after 1 or 2 classes. So Orth-Mover distance is a metric to compare two probability distributions. So in this case, let's say this P and Q, and it's defined in some metric space, and then the Wasserstein distance of order R is given by this. Okay, so this is the distance, Wasserstein distance of rth order, and so this is the small r there, and you see this r goes with the distance here, right? So dxy is some distance metric. Okay, we have seen that before, metric, and then pi here is the joint PDF. Okay, joint PDF with distributions, marginal distributions P and Q. So if you see this capital pi x, this capital pi x means set of all joint distributions, set of all, okay, it's already written here, sorry. Okay, so set of all joint denotes the set of all joint probability distributions on x cross x with marginals P and Q. Okay, so if you marginalize the joint, then with one, then you get the other. If you with the other one, then you get so. So this is a slightly different kind of distribution, right? You see here integration is being taken over d pi, and pi is the joint PDF, and then you are what you are looking for is this expectation of the distance in the joint PDF, right? So you can also write this as expectation of the distance. Okay. So another way to write, because this is like an expectation, but only thing is that the PDF is the joint PDF now, right? So this is your joint PDF. So this is like expectation of the distance xy. Okay. So this is how Wasserstein distance is defined. This is a distance, so it satisfies all the 3 properties of the distance: non-negativity, symmetry, and also the triangle inequality. Okay, so here dxy has to be some valid metric. So we have seen what a valid metric is. Just now I have defined, and for a special case, which is what we need here, is when r is 1. Okay, so that is the special case that we will look today, and then we will prove an interesting result called KR duality. Just like for GAN, we needed conjugates and then some interesting analysis to bring the supremum out, and that's how we got the supremum. And in this case, the trick that we need is something called KR duality. So again, Wasserstein distance as such is not tractable. As you can see, it's it's an infimum over all possible joint distributions, right? All possible joint distributions, and then you have to look at the integration of this guy. So this is not tractable in the current form, but after applying KR duality, it is tractable. Okay, so for our purpose, for generative modeling, what we really need is that P is the distribution for the original images, and Q is some parameterized distribution P theta. Okay, so just like in KL divergence, we were doing KL divergence of P with P theta. Here we are looking at Wasserstein distance between P and P theta. Okay, so that's the setup. So the thing that changes now is this distance measure itself changes. Okay, but more or less our approach is kind of similar, that we want to get to some tractable form where we can compute Wasserstein distance. So as I said, this is not tractable, and can we have a tractable upper bound? So this will give us tractable upper bound. It will look very familiar to you because something similar was seen in KL divergence. And in KL divergence, what we had is like you had f star t of phi, t of something, right? And then here you had a t here. Here it's slightly different here. Here you have h only, and then but here you are looking at those h which 2 norm is like less than equal to 1. Okay. So this will allow us to again, in the similar way like KL divergence we had, we will have similar parameterizations going on here, where h will be replaced by discriminator, and this x will be via push forward g theta of z, okay, where z is the known. So more or less the setup is there, but how do we know that WPQ is supreme of this guy is the main theme of today's class, where we will explicitly prove this result. And by doing this, you will get few intuitions that will help you in the algorithmic research in future. Rather than just using things, you might also discover a few ideas by yourself. Okay, so let us try to prove this. This is called Kantorovich-Rubinstein theorem, KR theorem. And what is very good about this theorem is that it says that the Wasserstein distance could be seen as difference of the expectations, okay, of some one Lipschitz function. Okay, so this is called one Lipschitz function, h1x, that satisfies this property. We call it one Lipschitz function. So this is the good thing about KR duality is the original in the raw form Wasserstein distance is not necessarily tractable, but this is also, we have to remember that this applies only to W1, which is like the Wasserstein with R1. Okay. So this is for W1 distance. Okay, so let us get to the proof now. So here from our setup, we know that Px is the marginal of the joint PDF, which is pi. So if I marginalize pi dy, that is, if you recall from the joint distributions in the previous classes, first 2 classes, then you are given a joint PDF. And then if you integrate out with the y, then you get marginal with x, and if you integrate out the joint PDF with x, then you are left with the marginal with y. So this is just the basic, we are trying to borrow from joint distributions. Then what we see from these two inequalities is that I can form an equality constraints. Okay, so that's where you can see where things are going, right? So I have 2 equality constraints now, h1x, which is px minus integral of ix dy. So this is something I have to satisfy, right? Because in Wasserstein, I'm only looking at those joint PDF whose marginals are p and q, and then I'm looking at the metric, the samples taken from those, and how far they are, okay, in some metric, okay. So this is a constraint that I have to satisfy because these joint PDFs should marginalize to P and Q. Okay, that's like that's part of the Wasserstein definition, right? Okay, so we have 2 equality constraints we have found. So WPQ is a minimization problem with equality constraints h1x and h2y. Okay. So we form the Lagrangian because this is a minimization problem with two equality constraints. So we can form the Lagrangian, there is only equality constraint there. So we form the Lagrangian. It's just that there are integrals involved, but nothing to panic here. This is our original objective. And then we have the constraint that this pi x marginalized to p and pi xy marginalized to p, and also with the q depending on which I'm integrating with. So those equality constraints have been taken care of here. So px minus integral of pi dx. So this is forcing the constraint that you are only going to have those pi which marginalized to p and q. Okay, and the role of the Lagrangian parameters are in our case. So in the original form we saw just in the examples that we had nu, right? So here we have two nu, but it's just that these are now functions now. Okay, rather than being a vector. So this is fx is a Lagrange multiplier now. It just happens to be function. Okay, there is nothing, no big deal here. And then another Lagrange parameter goes with other equality constraint. Okay, so these fx and gy are Lagrange multipliers, and this is the weighted sum you can see. So in integral it's a weighted sum, and this was our objective function that we had. Okay. Okay. So now what we will do is that we will rearrange the terms. So if you rearrange the terms, then what you see is if you collect these guys, px fx, px fx dx, then this is like as if you are doing integral of fx with pdf px. Okay, so this guy is nothing but expectation of fx only, and then similarly if you do qy with gy, so this is like sorry. So if I have to. Okay, so this is like gy and qy dy. Okay, so this guy is being written like an expectation of gy, and this guy is being written as expectation of fx. Got it? You can take time. Okay, so you are also learning the process. Okay, you are learning few things along the way. It's not necessary that you have to know everything. That's what I'm saying. Okay, so that's fine, right? It's just that it's a Lagrangian, but in integral form and things like that. So there is this additional extension that you did just now, right? So you may not have seen something like this, but you learned it right now. So we can do the Lagrangian, and then now we did the rearranging part is straightforward. And now the remaining one guys are here, which is easy to see, I guess. So the remaining guys are this guy, x minus y pi xy. So I can see x minus y norm pi xy, and then so pi xy and fx, right? So pi xy fx, negative of that is there, and then minus gy pi xy is also there. So minus gy pi xy is also there. So the second term is also okay. All right, so we have rearranged this term. So what do we see here, right? What we see here is that there are no inequality constraints, right? There were only equality constraints. All right, so there were only equality constraints, and the objective is convex. Then Slater condition holds by default. So if the Slater condition holds by default, by the Inf-sup equality that we have seen, that holds here, right? So Inf-sup of the Lagrangian is equal to the sup-inf of the Lagrangian. Okay, so that's what we immediately claimed here, that to help our computations a bit later on. All right. So given a Wasserstein distance problem, we had infimum of this guy over all the joint with marginals, but then we figured it out that we can force these separately as an equality constraints, and then form the Lagrangian, and then we see that that it's good to kind of reverse Inf-sup via sup-inf, and use the fact that the Slater condition holds by default, because there is no inequality constraint to check anyway. Okay, so there is a minor thing that will be left, let's say, as a minor exercise, I would say, minor or measure, I don't know, but but the point here is that there will be a problem like you figure out maybe as an assignment, and then we may discuss a bit more. So if we look at the previous term, what we have is 2 norm of x minus y minus fx minus gy, right? So now we are looking at cases where the fx plus gy is kind of greater than the 2 norm of x minus y. So basically this guy being positive or negative. Okay. So what we are saying is that we are going to leave out the negative ones because that will be troublesome. So that's like something to figure out why. I will give a small hint that if it is kind of negative, because 2 norm of x minus y minus fx minus gy, if it is negative, meaning this holds, then we can send the Lagrangian to minus infinity. Okay, so we can concentrate the mass of pi at xy and send it to infinity. So we leave it as an additional exercise to verify a bit later. Okay, so that I can complete the KR part, and we can discuss this again as an assignment, not as a main class. Okay, so so there will be a problem if it is negative. Okay, so so let us assume that it's positive. So let us assume that 2 norm of x minus y is greater than or equal to fx plus gy. So if that happens, so with this so with this the Lagrangian, the infimum of the Lagrangian is obtained by taking pi xy is 0. Okay, so the because the part that I'm going to integrate with, if it's a positive quantity, then the best way to make the integral 0 would be when I take pi xy to be 0. Okay, so this could be the minimum possible value of pi xy when I have so what did we do? So yeah, infimum. So if we look at the infimum of the Lagrangian, then what we have is this, right? So infimum is obtained when we have the second term, like the first few. I mean the second term, the pi xy and all those guys, right? The integral that goes to 0. In that case, we are only left with this supremum of this. This guy is greater than or equal to 0. So what we are saying is that if we have to really infimize this, then it's possible when pi xy is 0, because this is a positive guy to be integrated. So to make it completely 0, then we may choose some special pi xy which is 0, and so basically the infimum of this guy will be just this. That's what we claimed in the slide. And if we do so infimum of this, so that's why we use this trick, right? So we wanted to do infimum first and then supremum. So we did infimum, and then this guy goes away. Then we are left with only the first guy, and then if you do supremum afterwards, then you know that it's the Wasserstein thing, right? So this is like your P star or D star, whatever you want to say, right? P star or even D star, because the strong duality holds. So what we did as a first step is infimize, and we were left with this guy, and then we do a if we just write a supremum of this guy now, just this part, then it will be nothing but just the Wasserstein, because sup-inf of L was indeed the Wasserstein, right? So this is what we are trying to. Okay, so this was our plan, that we could do infimum first, then supremum, and that's where we stop, right? At least in the first phase, right? So this is clear, right? So sup-inf of the Lagrangian will be supremum of this guy, and this is good. This is good because you can see already we have some splitting going on, right? We have some f and g. Obviously, this is not the same h that I told you in the beginning, right? So the Wasserstein was like supremum of expectation of hx minus expectation of hy, right? This is where we wanted to go, right? So the and h1 ellipsis, right? So this is where we want to go, right? And what we see so far is this up to here, right? So there is f, there is g which is different from f, but here what we want to reach is h guy, and possibly they are allowed to be one ellipsis, okay? So what we have so far is there is some splitting that we did. Now it's with expectation with of some function with marginal p, and there is expectation of some function with marginal q, okay, and we can do supremum, okay, but we want to get to this this form now, okay. So we leave this for the moment, not leave, actually this is what we will use now. So for the lower bound of the W1, which is the Wasserstein with one distance, let us optimize over the class of one ellipsis functions. So let us see, this was our original thing, right? We wanted to go up to here, so we start with that, and let us see what we how it is, these guys are related to Wasserstein. So this is a interesting trick here going on. So these are the tricks sometimes people call sleight of hand, okay. So sleight of hand means like as if you're doing some magic tricks, and you will see that sleight of hand sometimes in most original proofs, like one or two interesting tricks are usually done. So let us see what trick is done here. Once I've written it down, it's not looking like that maybe now, but okay. So let us see what this guy is, right? Expectation of hx minus expectation of hy, okay, and this is what we wanted to go there, but we start from there and let's see how, I mean, how does it look like, right, in terms of Wasserstein. So by definition, expectation of hx is hx px, because this is expectation with p, so we put the pdf, and then minus of expectation of hy, and this is with distribution q, so we have the qy, so that's by definition of the expectation. And then what we did here is hx, and px was marginal of pi, right, with so marginal of pi. So px, this guy has been written like this. So if I marginalize the pi and integrate out the joint PDF with y, then I necessarily get the p, because that's how the pi were, right? And similarly, if I look into the other guy, then the same thing happens. So hy and then qy, I can write like this: marginal of pi joint PDF, and I marginalize out the x part, and that is actually the qy. Okay, and then what are we doing in the next step is we can write. What we can do here is we have so hx and hy, we can combine them now. So this will be hx pi xy, and then this is hx pi xy, hy pi xy. So we could combine them, and then we have pi xy, and this, there was a dx here also. So there was dx with this guy, and there was dy with this guy, right? So if you recall, sometimes you have a PDF, right? If you recall joint distributions dx dy, so usually it is double integral, right? With x and with y, right? So that's what is happening here. So these double integrals are now combined into this. So this essentially means this is kind of like double integral here, okay. So this guy is representing the double integral for x and y, okay. So that's a compact form that you have written here. So we have combined those double integrals, and we have hx minus hy, and both taken with pi xy dx dy. Okay, you could again split and go back, right? So the both are valid. Okay, I can split, take pi xy with hx and pi xy with hy, and do the split again. Okay, so so we have this guy, and what is the sleight of hand that I mentioned is that I can put an infimum on pi. Okay, and as you can see, I have not changed anything here. I just put an infimum in front, right? So I just put an infimum in front, and then it's like, how can I do that, right? How can I put a infimum without changing anything? So can you guess, right? Is it legal to put infimum just like that, right? So in other words, was pi did pi had anything specific here other than just indicating that it's marginal with p and marginal with q? Nothing. Okay, there was nothing specific about pi, as long as I have taken a pi which produces marginal with p and marginal with q, and that is what we have anyway. Then it doesn't matter, right, which pi I took. I took your pi 1, or somebody else pi 2. It does not have any role. So then this is called sleight of hand, right? So then I could have said that that it will be same as infimum value of some pi. Let us say pi star. It doesn't matter, okay? Because from here to here, pi, there was nothing specific. What was specific about pi was the marginals, but that was true for all the pi's we are dealing with anyway. So we could put the infimum pi. Now that's where it's interesting, because in Wasserstein we see the infimum, right? And that's how we needed this infimum guy to somehow reach to Wasserstein, because Wasserstein is infimum over this metric. Now these are one ellipses, right? So one ellipsis essentially means I can just define that H is one ellipsis if Hy, the mod of this, is less than or equal to norm of x minus y. This is exactly what one ellipsis means. If you want to generalize L ellipsis, you could put L constant here, but this is one ellipsis, so we say the constant is 1 here. So now we are optimizing over one ellipsis function, which is our H. Now this guy's H is one ellipsis, so that's why this guy is less than or equal to 2 norm of x minus y. Okay, let us say we are dealing with 2 norm. So 2 norm of x minus y, so that's why you see this inequality here. So this integral is now less than or equal to, because the integrand is less. If the integrand is less, the integral is less, obviously, right? So this guy is less than or equal to 2 norm of x minus y. Everything else remains the same. But voila, this guy was indeed our Wasserstein, right? This is, by definition, it was Wasserstein, right? So 2 norm of x minus y, W1, right? So W1 of the one, the power of r was 1 here for the metric. So this is x minus y pi xy dx dy. And what we proved is that if I optimize one ellipsis function and look at these guys, then they are necessarily less than or equal to WPQ. Okay, so what we have shown, we want to show that this is equal to this, right? So what we have shown is the lower bound. To prove equality, sometimes we can show it's less than equal, and then we show greater than equal, and then we conclude that it's equal. Okay, so we have shown one part that it is less than equal. So now so I have explained what I did about the infimum. That was the main trick here. You could bring in infimum that was needed for the Wasserstein, right? Okay. Okay. Now let us the previous one, the previous thing that we did, this guy, expectation of Hx minus expectation Hy, we have proved that it's less than or equal to WPQ, right? And that is true for all H. Okay, so we said that for any one ellipsis H, this guy always holds. So we can also say that since this is true for all H, it should be true for supremum over all H. Okay, so that's where we put here supremum here, and this denotes one ellipsis. Okay, so basically we have this, which is essentially the less than equal to part. Now we have to show the greater than equal to part also. So now we will show the following upper bound, which is when WPQ is less than equal to this guy. Okay, so we have seen greater than equal to, now we will show less than equal to. And so essentially what we have also shown as a as a preliminary result was this guy, if you can recall, when we do this inf-sup switch and we left it up to there and we said fx plus gy is less than equal to this, then in that case WPQ was kind of sup-inf of the Lagrangian, and if inf boiled down to just this guy, and then we are left with the sup part. Okay, so essentially what we are going to fill the detail here now is this guy. So let us see how this goes. So for this we will introduce something called Infimal convolution. So let us define a convolution like this, where some kx function is defined, which is infimum over u to norm of x minus u minus gu. Okay, so let us memorize this as some function that we have. We first claim that k is one ellipsis. Okay, so to prove the k is one ellipsis, we have to show that kx minus ky is less than equal to norm x minus y. Okay, so so let us look into the kx part. If you see the kx, then if you remove the infimum, then it's going to be greater than equal, right? So obviously this inequality is correct, because if I remove the infimum, this guy is going to be greater than equal. So that's fine. And what we did next, it seems like we have added and subtracted y. So if you see this guy here, so this is like norm of x minus y plus y minus u, and we deduce the triangle inequality. So this is x minus y plus y minus u. Okay, so we added and subtracted y furthermore to get this guy, and everything else remains the same. Okay. Okay. So continuing from are we continuing? So continuing from above, I guess above holds for any u. So yeah, let us see if there is a continuity or not. So kx is less than or equal to 2 norm x minus y plus y minus u minus gu. Okay, so this is like true for all u. So this is like true for all u. So it should be true for infimum over all u as well. So that's what we did. We did an infimum of the second part. Okay, so that was true for any arbitrary u. So it should be true for infimum of u as well. So that's what the only change we did, the second term here. And if we do that, then this infimum could be written as ky. That was the definition of the infimal convolution. The way we defined was indeed equal to ky, right? So ky, and then we so basically we have kx. We can rewrite, and so we can rewrite kx as less than or equal to 2 norm of x minus y, and this is like ky. And we can bring this ky on the left, because we are looking for ellipsis continuity, right? So essentially we are looking for k to be, this infimal convolution to be one ellipsis, and this is exactly what we proved, right? So we proved that the kx minus ky is one ellipsis, right? Right. So we are almost there. So now so, and similarly we can prove the other way also, that we can flip that. Okay, there was nothing due to symmetry. You can also say that I can also prove ky minus kx is less than or equal to 2 norm of x minus y. So if I combine both these guys, if I combine kx minus ky minus kx, we can say that the mod of kx minus ky is less than or equal to 2 norm of x minus y. Okay, so now we had this guy there, right, in the supremum somewhere. So we look at that now. So if fx plus gy is less than or equal to 2 norm of x minus y for all x and y, then for all v, so here what are we doing is fv yeah, this is true for all x and y. Then in place of x we put v, and in place of y we put u. Yeah, okay. So in that case we kind of instantiate this with x v and y u, and g we put it on the right. So then so let us do that. I think this step is missing a little bit. So this is like f. So in place of x I have v. So fv plus g u, is less than equal to norm of v minus u. So this is like fv is less than equal to norm of v minus u minus gu. Okay, so this is what this step means, and what we are saying is that again there is really nothing specific about u and v here. We could have taken or u here. There is nothing specific about this. Is true for all u, so true for all u. So if you take an infimum of this guy, then also it should be true. It is true for any arbitrary u. So for the one for which it has minimum, also it's true. Okay, so it's true for any u. So this is okay, and then what we realize is that this could be written as kv again, the Infimal convolution. So you see, we are trying to relate this f and g guy with the convolution, because convolution we know it's one ellipsis. So we are trying to reduce this down to this case. Okay. So basically fv is less than equal to kv. Kv is the convolution, right? And we can also instantiate u with v, because it's true for all, right? So when u is v, then what happens? We just reduce to minus gv, right? So these are the two things we have now. Okay, so for v equals to minus y, minus ky is greater than equal to minus g. Okay, so let's see. For v equals to minus y, k and g, right? Okay, so kv is less than equal to minus gv. That's what I see from here, because this guy continues from here, right? So kv is less than equal to minus gv. I guess this is going to be used. So v equal to minus y, right? So kv, okay, kv is less than equal to minus gv. Okay, so kv is less than equal to minus gv, and if I put v is minus y, v is minus y, but I wonder why if v is minus y, then how come the y will come out, right? I mean the minus will come out. So v is minus y, then kv minus kv. Okay, so I guess, okay, so we can multiply both sides by the minus 1 and just reverse this inequality. Let us see that first. So this is like minus kv is greater than equal to gv. Okay, so this is what we have. Now we can put whatever we want here, right? We can put v to be y also. It doesn't matter. I guess I meant v to be y only. I don't know why I put a negative there, but what we see from here is what we proved is kv is less than equal to minus gv. I just put v, substitute v by y, then we have minus ky greater than equal to gy. Okay, so okay, and this is how we relate to this guy now. Okay, so is it relatable, right? So minus ky or ky, right? So we can write this as ky because yeah. So let us look into this. So minus of ky is greater than equal to gy plus ui, right? So hence the expectation of the minus of ky is going to be greater than equal to expectation of gy. So that part is okay. Second part, and the first inequality, do we have kx is greater than equal to fx? I believe it was there. Okay, so kx is greater than equal to fx. Okay, so v I can put as x. So kv is greater than equal to fv. So in that case also kx is greater than equal to fx. Hence expectation of kx is greater than expectation of fx. So what you have seen is something interesting, is that your original thing was with fx and gy, and f and g were two different functions, and then what you have said is that this is less than equal to expectation of kx and ky. K happens to be one ellipsis, okay, and there is k and k both there. It's just that there is a negative there now, okay. So that's interesting. That's how we are going to one ellipsis now. So using this, we can now derive the inequality. So WPQ, we left it there, okay, remember that, and then expectation of x plus expectation of gy is less than equal to kx and ky. But again, I have done a slight thing, I hope you don't get confused. I replaced k by h, okay, so which is some convolution or one ellipsis, let us say. So in place of k, let us say some h. So this h x hy, and this is supremum over all one ellipsis function, this one, right? So this one, right, hx minus hy was less than equal to WPQ. We proved this, right? So this is less than equal to, right? So let us check that it was less than equal to is used. Yeah, so this is less than equal to. So this actually we proved it, right? So we have that this. So this is interesting, right? So we started with WPQ and we ended with WPQ. So this means that the internal the inequality must be equality, right? So in other words, we can now say that WPQ is equal now, okay? Because if you start with something and you say that it's less than equal to the same thing, then intermediate ones cannot be inequality, right? They all have to be equality. So, and hence we prove that WPQ is same as is equal to supremum over one ellipsis functions, and then difference of the expectations that you take, okay? That's Wasserstein for us, okay? So WPQ, that's the form that we are looking for. Now we can play around with parameterizations, okay? So we can do quickly the parameterization part is very easy, right? So you can already say, okay, let me put h as a discriminator, since discriminator is like a classifier, so I will put this like a log thing there, okay? So so log of the d phi, right? And then y that we see here, we see q as some parameterized distribution, right? So in this case, they are kind of parameterized by neural networks. So the y will be coming from some g theta, right? So let us quickly go through this. So from here onwards, parameterization is all you need. So here, recall in KL divergence, we had this, right? So there's a slight difference. We had f star, t, and so on. But there is a similarity, right? So now we have h and h, but one ellipsis. Somehow this makes GAN much better, okay, in performance. So so we follow similar steps. We replace h by some classifier loss, and then we replace y by some from discriminator. And if we use the notations of the original WGAN paper, then they write like this, okay? So, but it's very I mean, pretty much similar to what we have. In place of h, they have fw. So this is parameterized, and then in place of y, they have g theta, and z is like a known distribution that you can sample. So here, in place of h, again, as I said, it's fw. So this is what the original GAN paper said, and obviously, you need to do this one more min, right? Because what you are really doing is like this, right? So it is not like given the distribution, I am just computing the Wasserstein distance. I am looking for a distribution, right? So there is this minima over theta is needed. What is the good theta for which p theta is close to this? And obviously, from the theory, we had not here, but like this here, we had the max that comes with the Wasserstein thing, but then overall we need to reduce this WP p theta, so you have to do the minimization with theta, okay? So that's it. That's Wasserstein distance. So what we did is that we started with Wasserstein distance. We saw that it's not tractable because it needs infimum over all possible joint PDF and minimizing the distance and so on. We went for the KR dual form. It involved a little bit of tricks, but then with that we could get into some form. And this is the Wasserstein WGAN algorithm taken from the original paper. So this is exactly the form that they have, and and more or less everything remains similar to GAN. You will take real images as x, m of them. You take random noise, m of them. You build the expectations could be seen as a sample mean. So you compute the sample mean of the loss, and then here they are using RMS prop is another optimizer. So they do gradient ascent here for because these are the weights of the critic, the discriminator, and so they will do the gradient descent. And what they show is that they do gradient clipping. So because in WGAN these FWs are supposed to be one ellipsis, right? So to have that effect that it's one ellipsis, they do kind of gradient clipping. So if you see one ellipsis functions, gradient will be bounded, right? So it's like this, right? So basically, if you can, your gradient descent is like this, grad FW, right? So essentially, to have this effect that I'm looking for one ellipsis function, they clip the gradient, right? So they say that let me compress the gradient between certain. They don't necessarily use one. They have this C. They justify that it's okay to also bound it with some C. That C is 0.01 here. Okay. So this one ellipsis thing is numerically enforced by clipping the gradients, and other things remain the same. For the generator loss, you sample the M random noise. You have just the first, just the second term involved with the generator, and here you are doing the descent. So you do the descent with the negative here. So this is more or less WGAN. We complete the WGAN. In the next, we will try to see WGAN with gradient penalty, and that further improves the result of WGAN. And more or less, these are kind of state of the art. I will show you a lot of interesting results with the GAN-like architecture. It's as good as diffusion model. Okay, so the reason why we are studying many type is these guys are also equally good. Okay, so we will see. So it's not like only diffusion models are good. These guys are also good. Their samples time is very less. So so I will show you very state of the art results with the latest GAN. Okay, thank you.